So let's use calculus now to calculate the volume or evaluate the volume of oddly shaped objects. And it's not a giant leap to go there because we've just finished a unit where we discovered that finding the area of oddly shaped objects is pretty easy to do if you can find a function for each edge. So if I have two functions, f and g, and an interval x2 and x1, I can actually calculate the area of this oddly shaped object using calculus. Well, it's not a giant leap then to imagine I might be able to use calculus to find the volume of oddly shaped objects, and in fact, I can. And to demonstrate, I'm going to use this sketch of a pitcher. So I've turned the pitcher on its side, and I'm going to place it, center it on the x-axis of a Cartesian plane. So this is the x-axis, this is the y-axis. And then instead of thinking of it as an already existent pitcher, I'm going to imagine that there's some function of x so let's call it f, that looks like that, and then some region on the x-axis between x1 and x2, and that the pitcher is actually formed by taking the area between the function and the x-axis and spinning it around the x-axis. And so when I spin that around, you can imagine that I would create a three-dimensional shape by spinning the function around the x-axis. So essentially what I'm doing is I'm taking some area and I'm creating volume out of it. Now, this isn't something you've necessarily done before, but you've certainly taken area and produced volume. If you take the area of a rectangle, we know that the area equals length times width, but the volume of a rectangular prism is just the area pushed into some height, right? So we push it straight against another axis, and we create volume from area. In calculus with oddly shaped objects, we can do the same thing. We can take the area between a curve and the x-axis, we can rotate it around the x-axis, thereby pushing that shape into a volume, into the third dimension, and calculating a volume, which hasn't actually taken us very much closer to being able to understand how to create a volume or to evaluate the volume of this pitcher, but it definitely gives us an image of how we might get there. So let's replicate the same process we used for area and see if we can move it into volume. Well, remember when we were calculating the area of an odd curve, we first divided the interval from A to B into subintervals or subpartitions. So we would use delta x, right? So the width of each interval is b minus a divided by however many subintervals we want. So in this case, let's say we want, well, 1, 2, 3, 4, 5 subintervals. 1, 2, 3, 4, 5, 6 subintervals. So in this case, we're going to say that delta x would equal 6. Then we have to produce partitions to measure the height, and I'm going to use upper partitions. All right, so now we have 6 partitions, which are easy to calculate the area of individually. But remember, we're not looking to calculate area, we're looking to calculate volume. If I spin this tab around, so creating the entire picture, if I look at just what happens to this first tab or this first partition, when I spin that around the axis, what I end up getting is a disc. Looks like a little hockey puck, right? So when I spin that partition around the x-axis, I get a disk. And what's the area of a disk? Excuse me, what's the volume of a disk? Well, the volume of a disk is going to be the area rotated, or excuse me, is going to be the area of the surface times the height. So let's start with the area of the surface, this circle at the top of the disk. Well, the area of the circle is pi r squared, whatever the radius is, r, times the height, but we happen to know already that the height is whatever delta x is. Okay, well, pi r squared isn't very useful yet because I don't really know what r is. I don't know what the radius. Oh, wait, I do know what the radius is because the radius for this disk, this height, is whatever the f of, in this case, b is. And now I have everything I need to write the volume of this disk. The volume would be pi times r squared, which is just the f of b. In this case, I'm going to write the f of xi to keep it general. Squared, because it's a radius, times whatever delta x is. So let's look at another example. Let's look at a different partition just to make sure that we're really clear about what we're doing here. So suppose I want to find the area, or excuse me, the volume of the disk that would be created from this partition spinning around the x-axis. Well, I need to know the height or the radius of the circle for the disk. I need to know the width, and then I already have pi. So the volume here, well, let's give it a value. If this is a, x1, x2, let's call this x sub 3 because that's the radius of that disk, which would produce a volume of pi times the radius, f of x sub 3, squared times the width, delta x. And so what I've done now is created or found the volume of this disk. Right? So now I have another disk. So now I have two disks, and if I were to repeat that process all the way across the length of the vase, I would have 1, 2, 3, 4, 5, 6 disks that I could add together to give me the total volume, or an estimation of the total volume, which would be written algebraically as the sum of I equals 1 to n, in this case n equals 6, of pi times all of my radiuses squared times all of my subintervals. And so now at long last, we convert our estimation of volume to an exact volume by taking the limit as our partition size, or our number of partitions, approaches infinity to give us the exact volume of our pitcher. Okay, one last step. We obviously don't want to calculate these limits all the time. We want to use the antiderivative, right? So the limit as n values approach infinity, that's what antiderivatives or integrals is all about. And so we want to calculate the volume, or we need a formula for the volume, which would be pi times the antiderivative on the interval from a to b. So all I did was pull the pi out front of, and I'm going to use a notation change here. I'm going to use capital R of x instead of f of x, because what we're really talking about is the radius. And so our radius squared times our delta x. And delta x, of course, is just another way of saying dx. So let's use our new formula to calculate an actual volume. The region bounded by the graph of f of x equals x squared, and the x-axis between x equals 1 and x equals 2 is rotated about the x-axis. What is the volume of the resulting solid of revolution? So let's draw a picture of it really quick. So we know that the function f of x equals x squared is just a parabola in standard position, and we want to take the area between x equals 1 and x equals 2. and rotate that around the x-axis. So now let's calculate the volume of that solid using just the formula. The volume equals pi times the antiderivative from 1 to 2 of f of x squared. So just because x squared is squared doesn't mean we're not going to square the whole thing. So the radius squared dx. So that's pi times the antiderivative 1 to 2 of x to the 4th dx. So that's pi times x to the 5th over 5 from 1 to 2, which gives me pi times 2 to the 5th, 2, 4, 8, 16, 32 fifths minus 1/5, which equals pi times 31 fifths, which is better written as 31 pi over 5. So the volume, of the shape produced by rotating that area around the x-axis is 31 pi over 5. So we have time for at least one more example, maybe 2 examples. So the region bounded by the graph of f of x equals 1 minus the quantity x minus 1 squared, and the x-axis is rotated about the x-axis. Find the volume of the resulting solid. So it's clear I'm talking about a quadratic, and I've graphed it so we can have a look at it. It's downward facing, looks like it intersects at 0, not sure where the other point of intersection is. Of course, I can use my trace function, but we have to be able to do this by hand anyway. I'm going to look for those 2 roots. So I'm going to set my function equal to 0, and then I'm going to solve for x. So x minus 1 squared equals 1. Take the square root of both sides. X minus 1 equals plus or minus 1. And so x equals plus or minus 1 plus 1. That means I have a root at x equals 1 plus 1, 2. And I have a root at x equals negative 1 plus 1, 0. So if I sketch that graph now, well, I knew what it looked like already. I just didn't know where these points were. And so 0, in fact, the one I suspected is true, and the other root is at x equals 2. So now I have my bounds. I'm going to rotate this solid around the x-axis and calculate the volume. So V equals pi times the antiderivative from 0 to 2 of 1 minus x minus 1 squared, all squared, dx. Okay, that's crazy. I want to clean this up before I even try to do that calculation. So I have 1 minus x squared minus 2x plus 1. So negative x squared plus 2x, 1 minus 1 is 0, and then this has to be squared. So x to the 4th minus 4x cubed plus 4x squared. Okay, so I can work with that. Take the antiderivative. So x to the 5th over 5 minus x to the 4th plus 4/3 x cubed on the interval from 0 to 2. Which equals 16 pi over 15.